Okay, so in this video we're going to take a look at what is called the single-ended isolated forward converter. Essentially this is an isolated buck converter, and in a previous video we looked at the isolated buck boost converter, so that we called that the flyback converter. And so if you haven't seen that, that has some pretty useful sort of discussion on isolated converters and how they're related to non-isolated converters and all that sort of stuff. So if you haven't seen that already, I'll link that in the description below so you can take a look at that. And it might be useful to do that before we jump into this discussion here. So essentially this is a isolated buck converter, as I mentioned. So basically it's a step down function, right? And it's called single-ended because power only flows for one polarity of the primary side voltage. Now that means when the voltage is positive, for example, power will flow. When it's negative or zero, it won't. And so for that reason, we call it single-ended. Now the circuit as it's drawn is not complete, and I'm going to leave it this way for now because I'm going to prove to you through the analysis that it is incomplete, and we'll then introduce a part of the circuit that is fairly important. And it's not limited to this circuit, it's a general concept of electronics in general. So why don't we analyze this thing in general first? So we have when Q is on, right? So when this transistor here is on, let's say this transistor is on, you have Vp equals V1, right? So the voltage applied to the primary of the transformer equals V1 since there's a full path there. Okay, now Vs in that case will be V1 over N. And before I go on, you might think that this is exactly or looks very similar to the flyback converter, at least on the primary side. But one key distinction is the polarity of the transformer. So notice that the dotted terminals are both at the top in this case, so there is no inversion of polarity here. So that's why I'm saying this circuit is incomplete as it's drawn. So if it were just like a flyback, it would be reversed. We wouldn't really have many issues. But in this case, we'll see that we do run into some issues. In any case, when Q is on, you have Vp equals V1. And you have Vs equals V1 divided by N, right? Because that's stepping across the transformer. So then the polarity is positive on Vs, as I mentioned, and D1 turns on, right? So if Vs is positive, that forces D1 here to turn on. Okay, now if that's the case, then D1 has a positive polarity here. You'd basically, this D2 becomes reverse biased. Okay, and therefore it's off. So Vd in that case, the voltage across this diode, Vd is V1 divided by N. Okay, and that's what your output voltage would be in that case, because in a case like this, when you have this is open, this would act as a short for that sort of DC part, and you would end up having V2 equaling Vd, and the result would be that the output is V1 divided by N. Now I should also mention that, I mean, it's a sort of side note, but D1 is called the rectifier diode, and D2 is called the freewheeling diode, just because of the function that they sort of serve. And at this point, because there's a direct path between the V1 side and the V2 side, I2 equals N times I1, right? So there's no issues in that case because you have a direct connection between the transformer and the output I2, and so you have the turns ratio sort of amplifying the effect of the current. So I2 equals N times I1. Okay, so for now, why don't we imagine that we're ignoring the magnetizing current, okay? So ignore I mu for a second, and imagine that N equals 1. If you do that and you analyze the circuit, you'll understand that this is a standard buck converter at this point. And a non-unity N, meaning if N doesn't equal 1, it simply steps up or steps down the voltage and current. So it either boosts the current or the voltage, depending on the direction you're going in. So if we ignored the magnetizing inductance, we would see that IP and IS, both of them end up being 0 when the transistor is off. So if we imagine for a second that this transistor is off, if this transistor is off here, right, then what you'd end up having is IP and IS would both be 0 when the transistor is off because there would be no current. And if, or again, it's a hypothetical case when I mu doesn't exist, because there'd be no closed circuit, so there'd be no current flowing through the circuit, right? And so That's the case when magnetizing inductance is ignored. Now when that happens, D2 must turn on then to carry the output current, and VD ends up being 0, which corresponds to the part of the cycle when the shunt switch of the buck converter is conducting. So still drawing the parallel between this and the buck converter, right? But there's a problem because the magnetizing inductance does exist. And so when this is 0, you don't just have the currents immediately drop to 0. So you do have an inductor, and the inductor does carry current. And so the challenge here is that when I mu is non-zero, you need to have something in place so that when Q turns off, there is a path such that I mu is not discontinuous. Because we said if that inductor L mu doesn't exist, then you have no problem and it's a normal buck converter. But we do have that L mu because that's the whole point of isolate. Well, that's part of the consequences of isolation. So we have to include something so that when Q abruptly turns off, I mu has somewhere to go. Because in this case, we don't have the secondary winding forcing the transistor, or sorry, the diode on the secondary side on as we had in the flyback converter. So in this case, we have a bit of a challenge. And so to sort of circumvent this challenge, we have to add, or to sort of address this challenge, we have to add an additional part of the circuit. So if we want to, we have a couple of requirements we have to meet. So when I mu is flowing while Q is off, Vp must be negative. And the reason it must be negative is so that this current will decrease. And so what do I mean? So imagine just you have this part of the circuit, okay? So you have just this thing, you have just L mu. And I'm going to ignore the rest of the circuit from now, and I'm only concerned with this thing. And so when this I mu is flowing, right? So when Vp is positive, let's say Vp is positive. Well, let's not draw the next part there. Vp is positive. What ends up happening is I mu will increase like this, okay? But now, all of a sudden, when I open the switch or the transistor, and there's no provision, there's no external circuit there, I've abruptly given the current nowhere to go and something's going to get damaged. So now I need to give it somewhere to go. And while I'm thinking of this somewhere, or while I'm thinking of this solution, this potential solution as to how I can solve this problem, I need to account for the fact that once the transistor opens, this current should decrease. Because if this current doesn't decrease and it keeps increasing, well, we have a problem because it's going to increase indefinitely then. And not only should it decrease, but it should decrease sufficiently so that it's not staying above 0 in every cycle. So it should go back down to 0. Because if it doesn't, and it comes back up to, like, let's say here, so if it goes down to like there, then what's going to happen in the next cycle is I'm going to give it more current, and it's going to go a little bit higher. Well, that doesn't really look higher, does it? But it should go a little bit higher. So let's say it's a little bit higher, and then it'll go up, and essentially you'll get to a point where you've saturated your core, and you run into issues in that sense after. So how do we achieve that? To achieve a negative current, we have to apply a negative voltage, obviously. So this would be Vp, and again this is a rough sketch, and this would be I mu. So this would be positive V1 here. So this is positive V1, and this is going to be negative something. It's going to be some negative voltage. Okay, so we have to apply a negative voltage, essentially, when the transistor turns off, so that we can ensure that this current goes down towards 0. Well, it should reach 0. It should not stay above 0. So the voltage should be negative. The voltage should be negative enough to ensure that the current goes to 0, and we should also ensure that there's a path there. So we want to do that. I mean, sort of the simplest way we can think about this is, why don't we connect here a voltage source, hypothetical voltage source. How we realize it we'll look at after, and then a diode. Okay, and the voltage of this voltage source, let's call it has to be negative, remember, and we'll call it VC, let's say. And this diode we'll call D3. Okay, so we call this type of a circuit a clamp. Okay, and so let's assume for a second that I mu is 0 when the transistor turns on, and Vp is positive. right? So what you'll have is this current will increase as it does. Now we're thinking about this circuit. We're not thinking about the original circuit anymore. So now we have an updated version of the circuit, right? So if we have an updated version of the circuit, when the switch is closed, the transistor is closed, sorry, this will be positive. That's Vp. And I mu will start from 0, and it will increase linearly like this. Okay? Now, when the transistor turns off, I2 will flow through D2, and D1 is going to be forced to turn off. At this point, Is is going to be 0, and so I1 will end up being 0, but I mu cannot instantly drop to 0. So Is is the current through D1. That will go to 0 because D1 is going to turn off. That means I1 is going to turn off because the secondary winding current also went to 0. But this I mu cannot instantly go to 0 because it's flowing through an inductor, right? So what happens in that case is this clamp circuit that we've called it, this additional circuit that we've had, is going to give I mu a path to flow as soon as this Q turns off. So when Q turns off, I mu will instead flow through this D3, and that'll force this D3 on. And the purpose of VC here is to sort of fix the transistor drain at a certain voltage. Okay, and so the requirements here, as I mentioned before, is that I mu should be 0 by the time the next cycle starts. Otherwise, it's going to continue to increase and saturate the core. So you can kind of think of this almost like it's basically a discontinuous conduction, right? So this has to be 0 before the next cycle is applied, and so it'll go up like this again. And this is what I mu would do, and this voltage has to be negative here, right, to do that. And then once it goes to 0, because the switch is off, after the inductor current goes to 0, you'll see that Vp would end up going to 0 as well, because the inductor current has gone to 0 and it's no longer changing. So there's no change in the inductor voltage, or there's no voltage developed across the inductor, rather. So there's a requirement then, right? So I mean, we have to, if this has to happen, so we call this V1 and we call this minus Vc. If you have to make sure that the voltage goes to 0, then there's a restriction on what the voltage can be, right? So if we make sure then, the way we've done this in the past is we've looked at time integrals for how we can apply sufficient voltages to the circuit whenever we need to. So the time integral of the transformer should be equal, or the time integral primary volt seconds, they call it, of the voltage applied to Vp should be equal to the part where it's the negative, right? So the positive and the negative components should be equal, essentially. It's the volt second balance. It's the exact same thing we've done for all the other things. So basically what I'm saying is that this thing and this thing should be equal, right? But not necessarily that they should be equal. You want to have one slightly greater. So you want the negative to be slightly greater, and the reason for that is a practical one, right? So first of all, you want 1 minus d Vc to be greater than or equal to d V1. And the reason why you want it to be slightly, like you never want to be at this boundary, because being at this boundary would mean that the current would reach 0 just before the next cycle, right? So if you apply a sufficiently large negative voltage, which is what Vc is, then you would reach 0 at a sufficient duration before the next pulse is applied, which would ensure that your core resets. So the flux in the core would end up being 0. And that's kind of it's a requirement here again, because if you don't, then you would eventually your current would keep rising, and you would end up saturating the core, which would not give you the functionality that you want. So you want to set the clamp voltage to be a bit larger than the necessity for I mu to be 0. So this is the sort of inequality, but you want it to be greater than, this is the theoretical limit. In practice, you can probably set it to be 5 or 10% more to be safe, because I mean, you might have other circuit non-idealities that exist that might contribute to the sort of effect that, or sort of detrimental effects that you don't want to have. So the purpose for D3 though, because we included a voltage source, and so you might say, why did we include the diode, right? So D3 ensures that the current I mu can't reverse, and so the flux in the core is 0 at its minimum, right? So that it definitely goes that way, and then it never comes back and by any chance starts to increase the flux in the core again. So when D3 turns off, VP would step to 0, where it would stay until the transistor turns off again, which is exactly what you see here, right? So VP goes up to that, V1 goes down to this, VC. Once the current drops and turns D3 off, you see that this voltage would snap up to 0, and it would stay there until the next cycle. And in the next cycle, this would turn on again, and you would go through the exact same process, right? So it's a discontinuous conduction. You can see this, and this is sort of inherent in the topology. You need this to happen, otherwise, if it's a continuous thing, you would not get the type of functionality that you want to see. Okay, so this clamp we've shown here is one of many ways. I should just mention that as a practical note. This is an ideal version of the clamp, so you can realize this using a couple of different ways, and we can discuss those shortly. But before we get into that, we should also mention that the duty ratio is the control, as it always is, or not always, but usually is. So the duty cycle would be this duration here. So the duration between these two, you'd call dt, let's say. And then this thing you can call delta 1, and this one you can call 1 minus d minus delta, as we've done in the discontinuous conduction analysis videos. The reason I'm not going to get into too many details and derivations here is because for the most part it's the same process, and if we do that for every single converter in every single video, these videos will end up getting very long and complicated and unnecessarily complicated, in my opinion. But still, remember that the duty cycle is the control. You can apply the volt-second balance. You have this equation for VP, sorry, this waveform for VP. You have V1 here, you have this time, you have minus VC here. You know that this has to be 0 over, the average of this has to be 0 over 1 period. So you can calculate what the conversion ratio should be, what the duty cycle should be when you're operating in this type of a conduction state. So what we want to have is, when we're designing this thing, we say that the duty ratio is the control. And so we'll set VC such that I mu equals 0 in the worst case, right? So the worst case would be whatever the worst case of operation is given your control objectives. But again, we want to make sure, as we saw here, that I mu should reach 0, right, at this point. And so you set that according to whatever the duty ratio you expect to be. Let's say you have a power supply. The power supply should operate with a certain condition. That condition requires a certain duty ratio. So you set that duty ratio, and then you say that VC should make sure that if I'm using this duty cycle, this current should be able to reach 0. And you can calculate what this maximum current is based on the voltage applied. Again, the entire analysis that we've done for all the other DC-DC converters, it all applies here. So it's not like every converter is analyzed in its own way, right? But one thing to note is that the larger the duty ratio, so the larger that this thing here, this positive part becomes, the higher the positive average region, right? And that means VC has to stretch further down, right? So if we just imagine for a second that, for instance, let's say, let's try to draw it proportionally, right? So if the positive region, let's say, is 3 blocks this way, then in order to have the positive and the negative be equal, then this region has to be 3 blocks this way. And not just 3 blocks, it has to be at least 3 blocks. This is the theoretical limit. So in reality, this, in order for the average to be, or the sum of the averages to be 0, this would have to be something like this. So this part has to equal, or has to be greater than, or no, sorry, the positive has to be less than the negative in this case, right? So this is the sort of trade-off. So as dt, which is this thing, increases, so too does this area. So this voltage VC would have to be more and more negative, which is obviously difficult to achieve. So there's a trade-off there. So you probably would like to take that into consideration when you're designing your converter. So you usually pick VC based on the maximum duty ratio that you expect, and then D below that will automatically ensure that your requirements are met. So we've drawn some waveforms. Why don't we draw out a little cleaner version of the waveforms just to kind of get an understanding of what's going on. And so again, this is a sort of discontinuous conduction state. So why don't we call that the first region? Why don't we call this the second one? And then we can call this, maybe this thing, the third one, and make this the sort of case that we're considering. And so that'll be dt. And so the first thing we can look at is, let's say, VP. Okay, so this is the voltage applied to the inductor. So the voltage applied to the inductor VP would be V1 when the switch is on, or the transistor is on, sorry. And then it would be minus VC. And again, this is not drawn to scale, but it would be minus VC during this time, and then it would snap back up to 0, and then it would stay 0, and then it would go on like this. And so that's V1 here, and this is minus VC here, right? Because you have to apply negative voltage. So if you're doing that, the next thing we can look at is I mu. So this is the current in the inductor, right? And of course, we expect the current in the inductor to follow the sort of DCM shape that we're used to seeing. So why don't we first write I mu here, and it would increase to some value here. Let's say it increases to here, and then it would decrease down to 0, like so, applied by the negative voltage, and then it would stay 0 for that time, and then it would start to increase again. And again, you can calculate this slope, right? So you can say that this is V1 divided by L times dt, then you can calculate what the maximum is, you can do all that stuff. So all of that analysis still applies here. But we're looking at it more from a sort of qualitative point of view for this analysis, because again, it's redundant, and it would greatly increase the length of these videos, and there's very little value, in my opinion, to be gained from that analysis. Well, there's value in doing it, but not so much for just listening to it over and over again. You should actually do it. And so what happens when what happens to I1? So remember, I1 is this primary winding current, and this only flows when Q is conducting. So this only flows between 0 and dt, right? So it goes between 0 and dt. Let's say it's like this, and then it goes to 0, and then it goes 0 for the entire thing, and then it goes up again like this. And the magnitude of this is I2 over N. We should probably mention this is I1. Right? So this is the primary winding current. And I guess the other thing we can look at is IP, right? So IP is the current that is entering this transformer here, right? And so maybe I should be a bit more clear. IP is this current. So we had it drawn differently before. So IP is this current, okay? And so IP we can draw, and IP is a little, I guess IP is probably the most complicated out of all of them, although it's not very complicated at all. It's just when you think about what's happening, because there's a couple of different currents coming together and a couple of different things you have to consider. So what happens in this case is IP starts at some non-zero value, and the non-zero value that it starts at, let's call this IP, the non-zero value that it starts at is I2 over N, because this is when the switch is conducting. So when the switch is conducting, IP is equal to I2 over N. We established that already, because when the switch conducts, the transistor, conducts, this diode is on. That means this current is just the reflected version of this current here, right? Very straightforward. So if that's happening, then you can say that it would be I2 over N, and I2 over N would increase. So that would be sort of the starting point. It would then increase to a certain value, and that certain value, I guess we should also add that label here. So this value here we can call I mu P, right, just for the peak. And so that means this current here would be I2 over N plus I mu P, right? Because it's increasing by the same amount as whatever that voltage that's applied to it. However, when the transistor turns off, this current will not linearly increase down. Instead, it'll snap down, right? It'll snap down like this, and then it'll increase down sort of like this. Sorry, decrease down, not increase down. Decrease down like that. And this, not the perfect in terms of symmetry or scale, but it's okay. And so this is going to be I mu P, because I2 over N no longer flows through that IP anymore, right? Because what happens in that case is this D1 stops conducting and D2 starts to conduct. So I2 never makes it to this side anymore, right? So this one, like I said, is a bit more, I don't want to say complicated, but it's a bit more involved. It's a bit less standard, I guess, to see a current do that type of thing. And then, so it jumps up again. Sorry, it doesn't jump that high. It jumps up to this middle point here, and then it goes up like that, as it did in the previous cycle. But the thing to note here is that this current here, so this current here and this current here are the exact same. The reason the one at the bottom looks a little bit different is it's just skewed because, I have to also incorporate the fact that I2 over n and I2 over n plus I mu p have to be accounted for there. But when you look at the actual behavior, it's the same current. It's from I mu p going down to 0. Right, so that's what's going on in terms of the current. Now, I mentioned that there are a couple of other clamp circuits, right? So this is one clamp circuit. This is one way to realize the clamp. Another way to realize the clamp is you can use a Zener diode, right? So, well, not another way, like a practical way, because this is not a practical way, let's be honest. This is just a voltage source. What's the source of the voltage? We have to develop one, right? So you can have a diode like this, let's say, and that can be connected to, let's say, Zener diode. Zener diode would be drawn the other way, not that way. So the Zener diode, let's say like this, and so that would develop the voltage and give you the characteristic that you need. There's other ways to do it, like there are some active switch ways to do it, and so like you can have switches, you can introduce more transformers, you can introduce other circuits, you can use another a capacitor, for instance. So the way that you would use the capacitor would be something like this. So you'd have your diode connected like this, let's say. You would have a resistor here, and then you would have, let's say, a capacitor like this, and that would serve the same function, right? There's other ways you can have a third winding, right? So you can have, this transformer has 3 windings, and one of those windings is here, and then you can basically switch it in another way such that you can produce the voltage that you need there. Those are called transformer coupled clamps, and you have an additional diode there as well. So you would force the diode to turn on. So essentially what that one would look like is something like this. So, well, it's kind of confusing, I guess, but basically your clamp branch would look something like this. You would have the winding that would be connected to the same transformer that is responsible for all the other things that we're seeing. The direction of the winding would be reversed, and you would have a diode like this. And so this would be connected across, so this terminal and this terminal would essentially be connected across this terminal between this and this here, right? So they just take the place of the clamp, and that gives you another way. But again, that's more complicated because then you have a 3-winding transformer, and that could increase the size of the transformer. It could increase losses in the circuit. You might have a certain footprint requirement or something. And so there are other ways, clamp circuits. I mean, there's a number of ways to do them. There's the active clamp, which is another transistor basically, so you can switch that accordingly if you want to. But I would say that these two are probably the most passive and simple and straightforward to implement, although they do have their limitations as well. So we did quite a bit in this. This was a fairly complex, I don't want to say complex, but there's a lot going on here as far as switching and whatnot. But overall, I mean, we see the function is the same. So the buck converter, boost converter, buck boost converter, in general, direct and indirect converters are the foundation for all the things we've done here. So this is an isolated buck converter. We established first that it was that, and then we established that there is the need for this clamp circuit that we called it, which is just this diode and voltage source, so that we actually give I mu a path to flow through when Q is turned off, right? Because you can't have a discontinuous current here, otherwise you'll blow something up. And so we saw that based on all of this, that first of all, there's a diode that needs to be here so that we can ensure that all the current or that the flux of the transformer goes to 0. And we also saw that this should be a negative voltage. And the reason this should be a negative voltage is that you need the negative voltage to make sure that I mu goes to 0, right? Because if this is any positive voltage, then I mu is going to keep increasing, or it'll increase at a lower rate, right, depending on the voltage applied. And so the only way this can decrease is if you have a negative voltage. And then we established that there's this relationship, right? So if this part is 1 minus d, and this part is dv, or sorry, it's v, it's d times v is the average. What you then require is that this inequality be met such that you can ensure that this type of characteristic takes place. And again, this is the theoretical limit. So if you're designing something like this, do not set it equal to. Make sure there's like some 10 or 15%, I would say 20% is usually comfortable, sort of cushion margin that you give yourself, so that you can ensure that your current becomes 0 well before the next cycle. Again, if you can afford it, there might be some cases where you can't, but again, in most cases you should be able to design around it, make some other trade-offs to ensure that this current will decrease sufficiently. And again, if you're interested in what this current is, you can apply the same analysis techniques we've done before. So the rise of this current would just be V1 divided by L mu times dt. And so then if you want to know how much current you basically need to, or how much voltage needs to be applied in what time to make sure that this drops to 0, you can do that calculation very easily. It's just the reverse of what we just did, right? Then we looked at some waveforms about what the general thing behaves like overall, which we basically discussed throughout the entire video, but here we kind of formally visualized them, I guess. And finally, we looked at some some practical clamp structures, right? And so these two are probably the simplest to implement. This one would require an additional transformer. And then I mentioned there's some others like active clamps, which use additional transistors, which would increase the complexity of your control circuit, gate drive, and all that kind of stuff, because you'd have to now switch an additional transistor. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.